Okay, thank you. So thanks, Mariano. Thanks, Maria Antonietta, for ever organizing this session. I delight to present today the hyperspectral sensor technology, in particular Prisma and DESIS. We are using in a prime water project for improving the water quality mapping. I will speak thanks to the work coordinated on behalf of Prime Water Consortium, and here people involved in a presentation today. So the presentation today will start with an introduction. I will show you some methods we are developing, an overview of level 1 and level 2 products. In particular, I will show some data about the signal to noise ratio from Prisma and DESIS, as well as the retrieval of remote sensing reflectance, which is the key quantity for water quality mapping. Some example we are providing for identification of water quality parameters, and I will end with a summary and conclusions. So we all know that remote sensing of inland and coastal water is challenging, as this environment are a mixture of optically deep waters with gradients of clear, turbid and productive waters with varying bottom visibility. Karin early showed how changes can be the concentration in these systems. And we do have also the effect of optically shallow that further complicate the retrieval of water quality parameters. So to recognize all the features present in these systems, we do need enhanced spectral information, which allow us to develop algorithms for defined retrieval of water quality parameters. And in this case, hyperspectral data provide valuable data. As you can see from the graph, in waters we may have a lot of peaks and dips, which are a function of water components and their characteristics and concentrations. So having a continuous signal in the visible to near infrared wavelengths allows the algorithms to improve the retrieval. Then these systems, of course, include big lakes, but also ponds. We have not very big lakes in prime water, so we also need sufficient spatial detail. So since a while, we are using this graph on the left to show the processes that are typical of inland and coastal waters and near coastal waters, for which the temporal resolution is plotted in correspondence to the spatial resolutions. So with respect to the remote sensing technology, there is a wide opportunity from observing this system from space. Those graphs show, it's taken from a pretty nice paper, which is already dated so far. So you do not have here all the most recent sensor, but the concept is that we do have a suite of satellite for mapping the processes in inland coastal waters. In particular, if we are looking to look at phenomena at the special case of 1 kilometer, we may use ocean color radiometers, which are also used in ocean applications, which provide valuable data for mapping water quality at this scale. If we need to go at closer fine mapping, we may rely on time series from Landsat and Sentinel-2, as Karin already shown now a nice example using this data for long-term monitoring. And in this class of sensor, we may now include the hyperspectral sensors such as Prisma and the state-of-the-art hyperspectral sensor, also looking to the future, from which we can really obtain nice data. So with the particular case of Prisma and DESIS, which are now operating, what we can assess, thanks to the catalog system from both the Italian Space Agency and DLR, we can access to level 1 products, which means top of atmosphere radiances, as well as level 2 products, which means data that have been already corrected for the atmospheric effect. So on the graph, you may realize the disturbance of the atmosphere in retrieving the water reflectances as stored in level 2 products. And from this spectra, we may derive the water quality parameters by using algorithms that take into account all the spectral features typical of these systems. So with a particular case of water quality parameters, we may have different approaches. The state of the art is progressing very well in the last year in this field. Basically, in the project, we are using two approaches. One most based on band ratio indexes, if we do have some nice features to be used for the water quality mapping. Otherwise, we may also use fully physical bioptical modeling, which can be inverted with different techniques to retrieve the water constituents simultaneously. So in this slide, I show the main characteristics of the sensor we are using in the project from space, Prisma and DESIS. These are rather comparable in terms of spatial resolution. Both they have 30-meter pixel size. Prisma covers a longer spectral range up to 2,500 nanometers. DESIS is limited to the visible near infrared, but for water quality application, we do say that DESIS already provide a very good coverage. Of course, Prisma is orbiting over the Earth on a satellite platform. DESIS is working from the International Space Station, so the coverage, aerial coverage of this system are rather different. And based on this, also the acquisition over study area can be distinguished. So this is a nice slide, show an image gallery of some Prisma imagery collected over a series of near and inland water systems, in which you may appreciate the color of the waters and nearby coastal zones, which can be captured from space. And this is an analog image gallery from DESIS, again captured over water system, including coral reefs and Italian lake. This is on the bottom right, Lake Trasimeno. So this data can be assessed across the catalogs, which are provided by the space agencies. The virtual lab will dedicate some time on this. So I will go on fast, but by agreed on licenses and upon registration, we were able to discover this data. So the first evaluation, we evaluate the signal to noise ratio of these sensors in terms of top of atmosphere radiances. And we have concluded that both DESIS and Prisma have a signal to noise ratio which is comparable to Sentinel-2, which already is providing valuable data for water quality mapping. So we are happy to say that both of the system has enough signal to noise ratio for developing aquatic applications. And with respect to the level 2, we also have computed the noise equivalent reflectances as a proxy of the signal to noise ratio. We used Hyperion as a reference, which was a previous imaging spectroscopy from space, in which, based on previous studies of Brando and Decker, we do know that we should have a noise equivalent of less of 0.1% to develop water quality applications. So in case of Hyperion, we were able to derive the noise equivalent of 0.1% by deconvolving the imagery. But working with the new Prisma and DESIS, without any deconvolution of the signal, we do have already reached the limit, the threshold suggested by Brando and Decker to develop water quality applications. So without any filtering, both DESIS and Prisma, apart the shortest and the longer wavelengths, already have the prerequisite with respect to the noise for water quality mapping. So we are then evaluating the level 2 products in terms of water reflectances by using in situ data, which are mostly provided by the network IRONET OC for a limited number of bands, as well as by other instruments such as the WISP station, which instead is an hyperspectral in situ sensor. And based on this analysis, which here is just reported a few examples of the whole analysis we are conducting, we do have also some metrics about the accuracy of level 2 products with respect to in situ data. So this data basically, both in terms of level 1 and level 2, allow the water quality mapping. The agency already worked to demonstrate the utility of Prisma on the left and on DESIS, with DESIS on the right, about the capability of this system in provide fine scale mapping, for instance, on shallow water areas, in salt marsh inland waters, as well as in coastal oceans. We are running similar exercise. So in this slide, there is an example of the retrieval of simultaneously mapping of chlorophyllate, total suspended matter, and sedum, as well as the shallow water characteristics in terms of macrophyte covers, retrieved from Prisma in Lake Garda, the largest lake we do have in Italy, for which we do have also some in situ measurements as a comparison. We have recently worked to develop a mapping of phycocyanin concentrations. This is a work in collaboration with NESA, which is a partner of Prime Water, in terms of phycocyanin concentration mapping in Lake Trasimeno, which is in Italy, and the Curonian Lagoon in the Northern Europe, in which a new algorithm, which is a machine learning mixture density network, has been compared to the state of the art of phycocyanin algorithms mapping. And the slide shows the improvement of the method. This is another example with Prisma in the specific cases of Lake Molarga as a case studies of the project, in which, similar as for Lake Garda, we did the retrieval of chlorophyllate, TSM, and sedum, as well as the mapping of pixel with the presence of phycocyanin. And a similar example with DESIS, in which we also obtained the inorganic fraction of suspended sediment thanks to the hyperspectral information of DESIS. This is, to conclude, an example of Mantua Lakes, a very productive system of lakes, riverine waters, in which hyperspectral DESIS imagery provide a map of chlorophyllae, a specific case in the red box of phycocyanin concentration, and also the biomass of floating and emerging macrophytes. To know more about DESIS, I would also invite all of you to register to this workshop, which is happening at the end of the month. So the registration is still open. So to learn more about DESIS, this could be an opportunity. And to conclude, we may say that Prisma and DESIS have been successfully orbiting to provide level 1 products, which are consistent to other missions. Level 2, which are promising but show a variable degree of accuracy with respect to remote sensor reflectances, while the state-of-the-art of image processing chains need to further exploit for water quality mapping. We may also say that the Prisma and DESIS overall show promising data for water resource mapping, this always in cooperation with the existing missions. Thanks for listening to everyone.